In this video, we're going to be reviewing conic sections, which are the graphs of parabolas, circles, ellipses, and hyperbolas. So before we get into the standard equations of those different graphs, I first want to just remind us why these things are called conic sections. So if we go over to the following applet here, parabolas, hyperbolas, ellipses, and circles are called conic sections because they are the result of the intersection between this double cone here and a plane. So notice that the plane is currently intersecting my cone in a circle. If I change the angle at which the plane is intersecting the cone, notice now I have an ellipse. If I keep changing that angle, now I have a parabola. And if we change the angle further here, I'm getting a hyperbola. Okay, so that's why these things are called conic sections. Okay, so our goal within this material is to take a second degree equation. So that'll be something where I have both x squared and y squared terms, or at least an x squared term or a y squared term. I can't have both a and c be 0. So I have one of these second degree equations. And my goal is to be able to write that equation in standard form so that I can identify which of the 4 types of conic sections I have and then sketch its graph. So we'll start with looking at ellipses. So you will get an ellipse from one of these second degree equations if a and c, those are the coefficients of x squared and y squared, are the same sign, so either both positive or both negative. If a and c are also actually equal to each other, you'll get a circle, which is really a special case of an ellipse. So what's the standard form? Well, the standard form for the ellipse will be the following. We'll have x minus h squared over a squared plus y minus k squared over b squared is equal to 1. Okay, so when you have it in this form, then the meaning of these different things, h, k, a, and b, is the following. The center of the ellipse is the coordinates h comma k. The ellipse expands a units in the x direction from the center and b units in the y direction. Okay, b units in the y direction. Okay, and you may recall that this is similar to the equation of a circle. So for a circle, a and b would be the same thing. We could call those actually the radius of the circle. And so for a circle, this simplifies to x minus h squared plus y minus k squared, equals a squared, or in other words, equals r squared. Okay, so what do we mean by this expands in these different directions? Well, if I have an ellipse looking something like this, okay, there's my center. A here would be the distance from the center to an edge. A is our horizontal distance, so this would be b, the vertical distance, and a here would be that horizontal distance out from the center. So that helps us get our sketches. So let's look at an example where we're going to put one of these equations into that standard form. So here I have 16x squared plus 9y squared plus 32x minus 36y equals 92. I do notice that I have both positive numbers for the coefficients of x squared and y squared. So I think this will end up being an ellipse, but we want to go ahead and actually put it in this standard form. So notice that's going to involve completing the square twice here. So the first thing we're going to do is just collect those like terms. So put all my y terms together and all my x terms together. I'll factor out any constants that I have. So this is 16 times x squared plus 2x. And this is 9 times y squared minus 4y. Okay, is equal to 92. So I got to think about completing the square in each part. So for this x squared plus 2x, to complete the square, I would have x plus 1 squared. Remember, we do half of the middle term for the constant here. Notice that x plus 1 squared would be x squared plus 2x plus 1. So what I've essentially done here is add 16 to the left-hand side. So I'm going to need to add 16 to the right hand side as well. Okay, so what about completing the square on this next one? Well, I'm going to have y minus 2 squared. Notice that that gives us y squared minus 4y plus 4. So I've added 36, 9 times 4, to the left-hand side. So I also need to add 36 to the right-hand side. So when we add this 92 plus 16 plus 36 here, we get 144. Okay, so we're getting close to what our standard form is going to be. Oops. I get 144. Okay, so to get into our standard form, I want to have 1 on the right hand side, so I'm going to divide through here by 144, which happens to be 9 times 16. So I'm going to get x plus 1 squared over 9 plus y minus 2 squared over 16 is equal to 1. Okay, so now this is in standard form here, and we can see that the center is the point -1, 2, because this is x plus 1, so that's like x minus -1, y minus 2, so that y coordinate of the center is 2. A here was the what was being squared when we divided our x squared type term here, so we see a is 3 and b is 4. Okay, so we can go ahead and sketch this now. So let's see, our center is at -1, 2. So the center is here. I want to go horizontally 3 units away. 1, 2, 3 in both directions. Okay, to get some of the vertices. And then vertically 4 units. So we'll have something down here. And then let's see, 1, 2, 3, 4 up here. Okay, so with those vertices, I can go ahead and connect the dots here. Okay, and I get this nice equation of my, or excuse me, this nice graph of my ellipse. So we see that those vertices were the points 2, 2, -1, -2, -4, 2, as well as -1, 6. Okay. So that's what we have for an ellipse, and we'll see that throughout these different problems, we're going to regularly be using completing the square to help us get that standard form. Okay, so let's look at what happens for our hyperbola case. Okay, you're going to get a hyperbola if those coefficients of x squared and y squared are of opposite signs. Okay, and there's 2 different standard forms that we can have occur depending on whether your hyperbola ends up having a horizontal axis or a vertical axis. You know, just like we can have horizontal and vertical hyperbolas, parabolas, we can have horizontal and vertical hyperbolas. So our horizontal one, we're thinking looks something like this, versus a vertical one that's doing something like that here, will look like the following. I'll have the x term being the positive one, so x minus h squared over a squared minus y minus k squared over b squared is equal to 1. Okay, and if we have a vertical hyperbola, the standard form will look like y minus k squared over b squared minus x minus h squared over a squared is equal to 1. Okay, so the horizontal one has the x squared term positive, and the vertical one has the y squared term positive. Okay, so what are some other key factors here about what the HK and the A and B represent in this case? Well, the center is still HK. Okay, so that means that this point here, that would be centered between the vertices of the 2 sides of the hyperbola. So what about the A and the B? Well, if I draw the asymptotes that my hyperbola is actually following here through the center, the slopes of these asymptotes actually come from those values A and B. I can also look at a box here that the asymptotes are passing through. So if I have a box here where the top of the box would be touching the vertices here, and those asymptotes go through the corners of the box, then this is a box here That's 2a by 2b, where it's 2b vertically here and 2a horizontally. So we're going out a units horizontally and b units vertically. So that means that I'm looking at a slope here, like of this line here as being a slope of b over a for rise over run. Okay, so that has to do with the slopes of those asymptotes for our hyperbolas. Okay, so let's look at how we can use the standard form here to convert the following equation to standard form and be able to sketch the hyperbola that we know will be associated with this next equation. So here I have 4x squared minus y squared minus 24x minus 4y plus 28 is equal to 0. So because I do have the coefficient of x squared being positive and the coefficient of y squared being negative, I think this will end up being a hyperbola, but I want to know exactly what that hyperbola looks like. So I'm going to have to use completing the square. So I'm going to collect my x terms together. 4x squared minus 24x minus y squared minus 4y. I'm going to move the constant 28 over to the other side, so I have equals negative 28. We'll factor out the constants here, so I have 4 times x squared minus 6x minus y squared plus 4y. Okay, so when I do completing the square, I'm going to have x minus 3 squared, taking half of that middle term of 6. This would give me x squared minus 6x plus 9, so that means I'm adding 4 times 9, 36, to both sides here. When I do completing the square of this next term, this is going to be y plus 2 squared. That means that this comes out to y squared plus 4y plus 4, okay, which means I just subtracted 4 from the left-hand side, so I also need to subtract 4 from the right-hand side. So notice that this would be negative 32 plus 36 for a value of 4 on the right-hand side. So to get this into standard form, I need to divide everything through by 4. So notice we have x minus 3 squared minus y plus 2 squared all over 4 is equal to 1. Okay, so since I don't have anything here, I'm just, to make it look similar here, we'll put that first one actually over 1. Okay, so we see that the center of our hyperbola here is 3 comma negative 2. The value of a, okay, which comes from the one that's associated with the x term for the horizontal distance, would be equal to 1, and b here would be equal to 2. Okay, so before I start sketching it, I also want to determine whether this is going to be a horizontal or a vertical hyperbola. Since I do have that positive x term, this is going to be a horizontal hyperbola. Okay, so now we're ready to do our sketch. Let's see, let me move some of these terms here so we have a little bit more room for our sketch. So we did find a equals 1, b equals 2, and the fact that this hyperbola will be horizontal. Okay, so I'm going to sketch that center point, 3, negative 2. So that's 1, 2, 3, and negative 2 down here. Okay, it's going to be horizontal, so the vertices will be a distance 1 horizontally from that center point. So I'm going to get vertices, vertices here and here. Okay, so what about my asymptotes? Well, I said I have to go up 2 units, okay, to make that box that my asymptotes will pass through. Okay, so we're going up 2 units and down 2 units. Okay, so we have something that looks like this. So my asymptotes are going to pass through the corners of that box. Okay, going up 2 and over 1. These are my vertices, so now I can sketch my hyperbola, having it approach those asymptotes here and going through the vertices that I've sketched. Okay, so we see that we have a nice sketch of our hyperbola based on that standard form. Okay, so for our last example, we're just going to look at a parabola. So we're pretty familiar with parabolas here, but this is going to look at the parabola under maybe a slightly different form than you've seen parabolas given recently. We will get a parabola if either the coefficient of x squared or y squared is 0, so if we don't have both an x squared term and a y squared term. And we know that our parabolas can be either vertical or horizontal. Okay, so we'll get a vertical parabola with the following standard form. So this is 4p times y minus k is equal to x minus h squared. Okay, we're not going to worry too much about this p-value. There's some more details that we could get into with parabolas, but what we're just concerned with here is that if that p-value is positive, it'll be a parabola that opens upward, and if it's negative, a parabola that opens downward. Okay, for the horizontal form, we have 4p times x minus h equals y minus k squared. Okay, it'll open to the right for a horizontal parabola here if p is greater than 0, and open to the left if p is less than 0. Okay, so putting it into sort of a similar form to the other ones, instead of having a center, the HK in this case is actually the vertex of the parabola. Okay, so we're just going to look at one example of this parabola. So I have y squared plus 4y plus 8x minus 12 is 0. The fact that I don't have any x squared term there tells me that this is, but I do have a y squared, tells me that this will be a parabola. But to put it into the standard form, we're going to have to use completing the square. Notice that the standard form also has the x and the y terms on different sides of the equation, so we'll move the 12 minus 8x over here to the right hand side. When I complete the square, notice I'm going to have y plus 2 squared, okay, which would give me y squared plus 4y plus 4, so that means I would just added 4 over here, so I also need to add 4 to the right hand side. So I have y plus 2 squared equals 16 minus 8x. So we can see that this is going to be a horizontal hyperbola because I do have that y squared term, so I need the other side to be the 4 times some p here times x minus h. So I got to factor out that coefficient from x, so this will be equal to negative 8 times x minus 2. Okay, so we can tell that not only is this a horizontal parabola here, but we do have this p-value of negative 2 being less than 0. So it's going to be one of those horizontal ones that opens up to the left-hand side. We also see that our vertex will be the point 2 comma negative 2. Okay, so with that information, we can get a quick sketch. So I have the point 2, negative 2 here. I know it opens to the left. If I wanted to get slightly more information here, I could find where my y-intercepts are. And it turns out that I'll be hitting negative 6 and 2 when x is equal to 0. Okay, so that just gives me 2 points to plug in here. So it looks like our parabola is going to look like this. Okay. So this just gives us a quick overview of our different conic sections and our standard forms. Remember, the goal is to be able to take one of these equations, put it into standard form, identify it as either a hyperbola, parabola, circle, or ellipse, and then give a quick sketch of its graph. Let me know if you have any questions.